Hello there. Welcome to the first physics seminar for the VCE Summer School 2023, VCS 2023. My name is Sai Pamaraju, and I am going to be in charge of delivering two seminars that are pre-recorded for you to look through at your own convenience during the program. So my name is Sai Pamaraju. And if you have any questions or concerns relating to the content of the seminars, or if you have any feedback regarding the nature of these seminars, if you find a mistake or an error, if I've made an error somewhere, please feel free to reach out to me on this email, spamaraju@student.unimelb.edu.au. And yeah, those are my contact details, which I will be able to access. So I'm a tutor. I have been a tutor at the VCE Summer School for the last 4 years. And during that time, I've been tutoring specialist maths and physics predominantly, as well as a little bit of methods. So I am quite across most of the content of the study design for this subject. So the two seminars that I have prepared are focused on the first one is focused on special relativity, which is this one. And the next one will be focused on some fun and games with quantum physics, both of which form a key part of the exam at the end of the year that VCAR provide. So without further ado, let's just jump into the content of the first seminar for today, the first seminar for physics. So on the agenda today, I want to introduce the idea of special relativity. Now, what exactly about it makes it special? We'll find out shortly. And what that entails is it entails an introduction to special relativity alongside Einstein's two postulates. We'll find out more about these in a second. I will then compare relativity and classical physics. Classical physics being the more familiar Newton's laws of motion, F equals ma, all the boring stuff. So all the Suvat equations and blah, 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 and where they don't work. The third topic here that I wanted to go through is the most important one, the most important consequence of special relativity, consequences, I should say, namely time dilation and length contraction. We will see what all of those mean in the coming sections. I promise you this will be quite interesting if you are very keen to pursue a career in, say, astrophysics or physics in general, and knowledge of special relativity is super, super important. If you're not, let me just tell you that your mobile phone wouldn't be working if some clever people didn't know about special relativity in the first place. So let's get straight into it. So the first thing I wanted to introduce before we jump into any of the above mentioned content, introduction to special relativity, I want to introduce a key definition, and that is that of a reference frame. And the title reference frame is exactly as the name suggests. So what it is it's a set of coordinate system. It's a coordinate system relative to which we can describe the position and the time at which a particle is doing something. So it's a reference frame consists of a coordinate axis and an origin. So if from where you're sitting or standing right now, if you see a television screen, if you see a laptop screen directly opposite you, that's directly opposite you in your coordinate system. That's in your reference frame, for instance. So here I have labeled a particle A, which has coordinates x, y, z, and t. So x, y, z are the spatial coordinates in three-dimensional space, and t is the coordinate in time. So if you've noticed, I've used Cartesian coordinates here, and that is very typical for reference frames. We don't deal with any messed up coordinate systems like polar coordinates. For those of you who are doing spec wouldn't know what I'm talking about. They're a headache to deal with, so we use Cartesian coordinates. So the idea of special relativity is it deals with inertial reference frames. So coordinate systems which are not accelerating. And they're not accelerating, but they're also traveling at close to the speed of light. So they're traveling really, really fast at the speed of close to the speed of light, because nothing can exceed the speed of light, and the only thing that can go as fast as the speed of light is light itself. Bit redundant, I know. Okay, so special relativity describes how our laws of physics are different in this high speed limit as we get closer and closer to the speed of light. So that's what special relativity is. Okay, so what's the big deal about it? Why did Einstein make a huge fuss when he published his paper on relativity in 1915? So the special relativity is based on two basic principles, two fundamental principles. These are known as what are called Einstein's postulates of special relativity. And what Einstein said was that the laws of physics are the same in all inertial frames of reference. Okay, what does that mean? Well, suppose you were on a train. That's my very badly drawn train, by the way. Yeah, you can see why I didn't do arts. Didn't study arts. So, let's say you are on a train. You're on a train here. Inside of a train, all the windows are closed, all the doors are shut. There is no way that you can tell, you can tell anything from the outside world. And to someone who's standing on the side here, looking at this train go by with you inside of it, I don't know where you're headed, but this is you, the listener, and this observer sees this train go past at the really, really close to the speed of light. Unrealistic, I know, but that train's missing a wheel. Okay, so this train is traveling really, really fast, close to the speed of light. Here's a question I pose to you. How would you be able to tell whether you're moving or not? How do you know if you're moving or not? If the train is traveling at a constant velocity, constant speed, can you tell if you're moving or not? In the frame of reference of the observer, you are, because the observer sees that train going past him. But as far as you're concerned, you're stationary. And if you were to see the observer by opening the window, you would see them going backwards. So as far as you're concerned in the train, the observer is the one that's going back in the opposite direction at the same speed. So the idea of the first postulate is that there is no single experiment that you can do that can differentiate whether you're moving or whether you're stationary in an inertial reference frame. So that's what the first postulate says. All inertial frames of reference are equivalent. There's no way of telling inertial reference frames apart. That's the first postulate. The second one is a little bit easier to understand. And it is the fact that the speed of light, which I'll label c, because that's conventional, E equals mc squared. C is the same for all observers, regardless of how fast or slow the source of light is traveling towards them or away from them. So it has a constant value of 3 by 10 to the 8 meters per second. So that's 3 with 8 zeros at the end of it. So ridiculously fast. For those of you who thought Usain Bolt was the fastest thing that could happen to mankind. No. Okay. So those are the two fundamental postulates, and they are absolutely essential to understand before making any more progress with this topic. And generally VCA exam questions tend to ask, state Einstein's two postulates of special relativity. And if that question ever comes up, this is your answer. The laws of physics are the same in all inertial frames of reference, and the speed of light is the same for all observers. And these are the fundamental building blocks of the theory of special relativity for the nth time now. Okay, so what is a consequence? A consequence of special relativity of taking into account this this different approach of thinking by Einstein, is that the way we measure quantities, especially times and lengths, in two reference frames, is not going to match up. Two reference frames that are moving relative to each other, they're not going to have the same perception of time and length. So we'll compare, we will see exactly how this works, and this is precisely the purpose of time dilation and length contraction, which are just coming up. But for now, let's just focus on the difference between relativity and classical physics, the approach of relativity versus classical physics. So classical physics is what I'm calling what Newton's laws are, what Newton said. That Newton, that the apple fell on his head and whatnot. What Newton says is that times and lengths are the same for everyone in all reference frames. Essentially, this is what he said. There is no, everyone measures time the same way. Everyone measures distances the same way, regardless of whether they're moving or whether they're not. That's Newton. What Einstein says is, hey, the way we measure times and the way we measure lengths vary depending on where we're doing the measurement from and how fast it's moving. Is it moving really, really fast, or is it moving really, really slow? So it's highly a relative quantity. Time and length change relative to who's measuring them. The perception of time and length, that is. So it depends on the reference frame from which that measurement is made. Okay, so as I promised, let's jump straight into time dilation, which is the first consequence of how time and length, how the measurements of time and length vary in the approach of special relativity. And for this, I have a little analogy. Suppose you're on a rocket. You'll be doing a lot of traveling by the end of this lesson, I'll promise you. So you're on a rocket, you're traveling in the sky at a really, really high speed. Let's say this rocket has a window, which I've drawn here. You are person A, and you have a clock on your rocket, a clock. So a clock which measures the time. Now, because you like fast rides, let's just assume that you're traveling at a speed that's really, really close to the speed of light. Okay. Now, let's say your friend, observer B, stands on the ground watching you as you go past it at close to the speed of light. And your friend has a clock as well, which measures the time. This is the so-called stationary observer, in inverted commas, because who really is stationary, right? Who is stationary? Well, it depends on who's measuring, whose perspective you're looking from. So, to illustrate that, consider person A in this rocket. As far as person A is concerned, they are stationary, and person B is moving backwards because they're stationary. They're not moving. Person A is not moving. But as far as person B is concerned, they are stationary. Person B is stationary, and person A is going across the sky at a speed close to the speed of light. So who is stationary and who's moving depends on who's doing the measuring, where you're measuring from. In any case, the clock in the stationary reference frame, in either case, whoever's stationary measures proper time, which I will label T0. T0 is what's called the proper time. And the proper time is the time that it takes, the time measured in the rest frame is what we call it. So time measured in the rest frame. The time that is measured in the rest frame of whoever's measuring. So if you're the observer, your clock measures the proper time, and if you're on the spaceship, your clock measures the proper time. So it depends on whose perspective we're looking from. And conversely, the clock in the moving reference frame measures what's called the dilated time. Dilated time. So for them, they measure, it appears as if they measure a slightly longer time compared to what you do. Dilated means stretched out. So time supposedly stretches out for them in your perspective, from your perspective. So how are T prime and T naught related? Proper and dilated time related. They're related by this seemingly simple mathematical relationship. So T prime is equal to gamma times T naught. Now this gamma is a very special number. It's what's called the Lorentz factor. And the way it's defined is it's defined as 1 over the square root of 1 minus v. V is the speed at which the object is traveling. V is the speed of the object. And c is the speed of light. Note that the Lorentz factor does not have any units. This is what's called a dimensionless quantity. So it does not have any units. No units. No units. So you could have a Lorentz factor of, say, 7, which is close to 99% the speed of light, just off the top of my head. If you're confused as to whose time would be slower, just think of this in this way. Moving clocks run slow. That's a saying that you can repeat to yourself. Moving clocks run slow. So the person on the spaceship, from your perspective, would have from the perspective of the stationary observer, the person on the spaceship would have a slightly longer time. They would measure a slightly longer time as far as, yep. So the moving clocks run slow. That's what it is. So that's one consequence of time dilation. One consequence of special relativity, rather, is that of time dilation. Another very similar consequence is what's called length contraction. So the time that we measure between things happening in relatively moving frames is different. The perception of time is different for people in 2 different inertial frames. And that's the same for length contraction as well. So, the lengths that we measure are also going to be different in different reference frames, depending on where we're measuring from. So let's go back into our spaceship. Your person A, you, the viewer, listener, and your friend is person B. This time, instead of a clock, you have a ruler. Now, once again, you're traveling at v close to the speed of light because you love thrilling, fast rides. So v is approximately the speed of light. So you're going really, really fast. No question about that. Okay, so the length that the person measures in their stationary rest frame is what's called L naught, which is what's called the proper length. This is what's called the proper length. Did I describe proper time up here? Yes, proper time, of course. Proper length. This is a common word, so please, it's a common bit of physics lingo. Proper things, proper length. So proper, the term proper is used when you're doing measurements in the rest frame of the object that you're measuring. Similarly, the length that you measure in the moving frame of reference is what's called L dash. This I will refer to as the contracted length, contracted. So you can probably imagine what happens when objects travel really, really fast from the perspective of a, so moving objects appear shorter, contracted. They appear contracted to an observer in their own rest frame. Okay, I know this is quite challenging to explain sort of verbally, but I'm doing my best here. Here's the thing. Here's the relationship between the dilated and the proper length. So L prime and L naught, which I've labeled. Contracted length. Sorry, did I say dilated? No, I meant contracted. The contracted length and the proper length are related by the following relationship. So L prime is equal to L naught divided by gamma, where gamma here, once again, is our Lorentz factor, which was described above. It's that unitless quantity, which is defined as 1 over the square root of 1 minus v squared on c squared. I defined this earlier in the time dilation section here. So v is the speed of the object, c is the speed of light. All right, so we know that as things get faster and faster, closer to the speed of light, when we see things going really, really fast, in principle, we could see, we could measure longer times between things happening, and also things getting shorter as they go faster than the speed, close to the speed of light. Where is this important? Why is it relevant? A key application of that is in the field of particle physics. So generally, we in particle physics, we smash particles together at really, really high energies, at really, really high speeds, close to the speed of light. And in that case, Newton's laws, F equals ma and Suvat equations and all the rest of it, they break down. We simply can't use them because they don't describe motion at such a high energy and at such a high velocity. So it's important to consider the effects of special relativity. And I said at the start of the video that that your satellites and your mobile phones wouldn't work if it wasn't for the principle of special relativity. So please do keep that in mind. So you can credit special rel for your Snapchat or something working. Okay. So here's an exam question from 2017. Actually, this is the 2017 VCAR exam. This is the one that I did. If you want to work out how old I am. Okay. So what it says is tests of relativistic time dilation have been made observing the decay of short-lived particles. So a muon traveling from the edge, so a muon is a heavy electron, a muon traveling from the edge of the atmosphere to the surface of the Earth is an example of such a particle. To model that in the laboratory, another elementary particle with a shorter half-life is produced in a particle accelerator, and it is traveling at 0.99875 C, gamma equals 20. So the Lorentz factor, they've given you the value. You don't have to work it out yourself. Scientists observe that this particle travels 9.14 by 10 to the minus 5 meters in a straight line from the point where it is made to the point where it decays into other particles. It is not accelerating. Okay, so straight away, we know that this is not, this is an inertial frame, which means special relativity holds. Okay, so we want to find the lifetime of the particles in the scientist's frame of reference. And if I were you, I would encourage you to pause the video and give it a crack on your own before you resume the video and have a go at the solution. So I will give you maybe 10 seconds. Okay, I'm assuming you've had a go at it. So we know that the particle travels 9.14 by 10 to the minus 5 meters in a straight line from the point where it is made to the point where it decays into other particles. So our proper length in this case is 9.14 times 10 to the minus 5 meters. So we know how fast is it traveling? Well, we know that it's traveling at 0.99875 C. Cool. So in that case, we can find out, because this is the distance that the scientists measure. We just want to measure, we just want to work out what the lifetime is. So this is simply an application of speed equals distance over time. So we're solving for t. So speed is equal to speed is 0.99875 and d, well, the distance is 9.14 by 10 to the minus 5, and t is that. So t is down there. If we rearrange that, we get that t is equal to 9.14 by 10 to the minus 5 over 0.99875 c. I've left c as it is, but it is equal to 3 by 10 to the 8, as I had mentioned earlier. So feel free to whip out a calculator and have a look at how and plug and chug this. So what do we get? We get that it is equal to approximately 3.05 by 10 to the minus 13 seconds. Okay, well, that's so that's fine. That's our proper time as measured by the scientists. So that's okay. So this is our proper time in the scientist's frame. Gosh, my handwriting's bad today. Okay. And because we're doing a VCA exam, we have to write the answer in the box, otherwise they don't look at it. Okay. Secondly, we want to calculate the distance that the particle travels in the laboratory as measured in the particle's frame of reference. In the particle's frame of reference. So we've been given the length in the scientist's frame of reference. So the scientists see that it travels at 9.14 by 10 to the minus 5. So what would the particle see? Well, in that case, we can just write down the length contraction formula. So L dash equals L naught over gamma. We know that gamma is equal to 20 because that's given in the question up here. So gamma is equal to 20. Now, so what are we trying to measure? We are trying to measure L naught, aren't we? Yes? Or are we trying to measure L prime? We are trying to measure L prime because we are looking at how much the length contracts. So in that case, what we have to do is we measure our contracted length. In that case, we have L dash equals 9.14 by 10 to the minus 5 over 20. So the particle in its own frame will cover a shorter length, will cover a smaller distance, if you like. So so the shortest length that you can measure would be in your own frame of reference in this case. So the proper length is shorter. Okay, so the 9.14 by 10 to the minus 5 over 20 is approximately equal to 4.6 by 10 to the minus 6. This is just me plugging it into my calculator, which you can't see here. Okay, so 4.6 by 10 to the minus 6. So that's that. Okay. So that's generally how a question on special relativity comes up on the exam. You have things like we have both time dilation and length contraction that are examined generally. Okay, so as far as the content goes, that's all for this seminar. If you do have any questions or concerns about any of the content in the seminar, or if anything is unclear, please do not hesitate to email me at this address. So that's spamaraju@student.unimelb.edu.au. Other than that, that's all I have to say. It's been a pleasure delivering this seminar for you, and I hope to see you in the next one, where I will discuss fun and games relating to quantum physics. See you then. Bye bye.